My name is Jackson Brzezinski, and I'll be presenting some recent results from Atlas on our improved track reconstruction for long-lived particles ahead of run 3. So first, just a little bit of background. What are long-lived particles and why should we care? So there's many beyond standard model scenarios which either predict or at least allow for particles with macroscopic proper decay lengths, which we call long-lived particles, or LLPs for short. So these range from various neutral naturalness and hidden sector scenarios, which can often give you exotic Higgs decays to long-lived scalars or dark showers, things like this. Various seesaw models, which can give you long-lived heavy neutral leptons, as well as various R parity violating supersymmetric scenarios. And so these searches for these kinds of signatures are notoriously challenging at detectors like Atlas or CMS, which are designed both from the detector standpoint as well as the reconstruction software to reconstruct prompt particles, or particles decaying close to the primary interaction point. So this has led to significant gaps in experimental coverage and unprobed phase space basically for these kinds of signatures. So this is exciting because it means that there is strong discovery potential for starting to probe some of these more exotic scenarios. The Atlas inner detector provides coverage for a wide range of long-lived particle lifetimes, simply by virtue of the exponential nature of particle decay, giving you the highest density of decays close to the primary interaction point, so in the inner detector itself. So this means that having a track reconstruction that is capable of reconstructing displaced signatures in the inner detector is essential for achieving sensitivity to various long-lived particle signatures in the inner detector, including displaced vertices, displaced leptons, more exotic things like emerging jets, etc. So this is where large radius tracking comes into play. So large radius tracking, or LRT for short, is an additional inner detector tracking pass in Atlas that is run after the standard track reconstruction. It is run on hits that are left over from the standard tracking procedure with a set of modified tracking cuts. And so you can see in this diagram here, a little schematic where you have standard tracks that are formed from these blue hits. And after the standard tracks are formed, you have some of these pink hits that are left over, which can then be used to form additional tracks that would have failed the standard track selection criteria. And so this algorithm is optimized to reconstruct the charged particles that originate from long-lived particle decays. This is a crucial component of many long-lived particle searches, those that are based around inner detector scenarios. And with interest in long-lived particle searches growing in the community, this is becoming an increasingly important aspect of the Atlas search program. So the algorithm itself is based off of the standard Atlas track reconstruction with several modifications, most notably the relaxing of the transverse and longitudinal impact parameter cuts, with the D0 max being relaxed from 5 millimeters all the way out to 300 millimeters to accommodate these displaced tracks. So what's new for LRT in run 3? So first of all, the run 2 LRT implementation was optimized for a high reconstruction efficiency, with the downside being a very high fake rate and a very high just overall rate of tracks being reconstructed, which prohibited LRT from being run in the standard track reconstruction. And so what this meant was that a special data stream was needed, which I'll talk about the implications of in a few slides. In run 3, this was completely re-optimized instead for fake rate reduction as well as CPU time to try to allow for this to be run in the standard reconstruction while maintaining a good efficiency as well. And so this was done by basically rethinking every step of the track reconstruction and trying to re-optimize these cuts that we placed for fake rate reduction. And so this was done with an emphasis on the earlier stages of the track reconstruction to prevent these poor quality seeds from wasting CPU cycles downstream and going through the track finding and ambiguity resolution, et cetera. And so most notably, this included now only using SCT hits for seeding as opposed to SCT or pixel seeds, which was found to significantly reduce increase the purity of the track seeds, changing the order in which the seeds are ranked to determine which seeds are processed first in the downstream stages of the reconstruction, as well as requiring the 3 space point seeds being confirmed by a 4th seed. And then there are also several other cuts like tightening the road width, chi-squared, et cetera, that also were found to significantly increase the purity of our track reconstruction. So now the end result of this optimization was a 95% reduction in fake tracks with only a 10 to 15% reduction in the signal efficiency, which translates to something like a 400% increase in signal to background for signal searches. So what this means is, we already saw this plot yesterday from Michaela, but that this run 3 standard tracking with LRT enabled is actually now faster than the run 2 standard tracking alone. So you can see this as a function of mu here, the green being run 2 reconstruction, which did not include LRT, and the blue being the full run 3 reconstruction with LRT. And you can see that at high pileup, especially, we've increased the speed by roughly a factor of 2 with respect to the run 2 reconstruction. So this is huge because it then allows for LRT to be run in the standard run 3 reconstruction and still having an increased tracking performance with respect to run 2. And just to put some of the rates in perspective, if you look at the number of LRT tracks as a function of mu for a simulated T2 bar sample, you'll see that LRT accounts for roughly less than 10% of the total number of tracks on average, indicating that the fake rate is well under control. So what does this mean for analysis? As I mentioned, in run 2, LRT was not run in the standard reconstruction, and we instead rely on this specialized data stream. So you can see this in this schematic here, where the workflow relied on these so-called filters, which are essentially a third level offline trigger, to pre-select roughly 10% of the raw data for downstream reconstruction with LRT. And what this meant was a significant amount of effort by analyzers to both develop and validate. Like I said, it's like developing a whole new trigger. A dedicated reprocessing of large amounts of data, which used an enormous amount of both person power as well as CPU time. We did not have LRT available in our standard model background Monte Carlo, unless specifically requested. And so we were generally forced to make do with what we had or go through small stats, MC requests, et cetera. And all this together seriously limited our analysis sensitivity and flexibility. So now in run 3, as I mentioned, LRT will be run by default as part of the standard reconstruction. So now we no longer have this specialized reconstruction chain. We just have one pipeline here, which means that there's no longer any need to develop these analysis-specific filters, which makes it much easier to R&D new ideas. We have significantly increased flexibility in analysis strategy, making it much easier to quickly turn over new analyses. We have MC LRT by default now in our Monte Carlo, and additionally, it allows standard analyses to also make use of LRT tracks to try to gain some boost there. And this is being investigated, for example, in the B-tagging community. So now looking at some of our performance plots. So we have here 2 samples, one of a displaced hadron sample originating from an exotic Higgs decay, as well as a displaced lepton coming from a displaced heavy neutral lepton. And we can take a look at the efficiency that we see as a function of truth particle D0. So what we're looking at here is what we call the technical efficiency, which is the fraction of quote unquote reconstructible truth particles that are matched to an LRT track. So these are required to pass truth level cuts that are, that could in principle be reconstructed by the LRT algorithm. So that includes at least 8 silicon hits as well as PT greater than 1 GeV. And you'll see that as a function of D0, the LRT recovers the quickly dropping standard tracking reconstruction efficiency after about 5 millimeters. And all the way out to 300 millimeters, we have quite good track reconstruction efficiency. And you can see zoomed in over here, the transition region between LRT and standard tracking, where you can see right at 5 millimeters, LRT picks up and quickly recovers this, this falling track reconstruction efficiency. Now, to kind of see how this works and what it looks like on a more high-level analysis level object, many analyses using LRT make use of an additional secondary vertex reconstruction, so we can quantify the impact of this new LRT on what an analysis object might look like. So unsurprisingly, a large number of LRT fakes translates directly to large combinatorial fake vertex backgrounds. And particularly for light LLP signatures like those originating from exotic Higgs decays, these fake vertices can be very challenging to reject because they mimic very closely your signal vertices. And so let's digest this plot a little bit here. So in purple, we have the run 2 reconstruction, and in orange is the run 3 reconstruction. The the markers are vertices that are matched to true long-lived particle decays. And the histograms here are vertices that are predominantly composed of fake tracks. And so if we compare the purple to the orange, the run 3 to run 2, you'll see that we have roughly 10 times fewer fake vertices, particularly outside of the pixel detector. And actually a slight increase in the signal reconstruction efficiency, which is interesting because despite the tighter LRT cuts and this 10 to 15% reduction in signal efficiency, the dramatic reduction in fake tracks leads to a significantly cleaner vertexing environment, which allows for you to more accurately reconstruct your signal vertices. So this is expected to translate directly into very large analysis gains for analyses using displaced vertices in this way. So now we can turn towards looking at how this performs in data. We have a totally new algorithm. We want to look at how this actually looks like in data. So what we're looking at here is the run2 data 2018 that has been reprocessed with the run3 reconstruction software. And these are zero bias data events. We're comparing this here to simulated samples of inelastic proton-proton scattering events. And so this is an inclusive, unbiased sample that we can use to probe the LRT performance. So after normalizing our simulation to the data by the total number of reconstructed LRT tracks, across the board, we see extremely good modeling in many different low-level tracking quantities. And so here on the right is the D0 distribution. You can see that the simulation very closely matches the data at the 5% level, all the way out to the maximum D0 of 300 millimeters. And it's worth pointing out here, these features that we see in the D0 distribution coincide with the radial positions of the 3 innermost active tracking layers. And these are a result of low PT particles produced in secondary material interactions. And we can see that this is captured quite well in the simulation. Looking now at some of the other low-level track quantities, we have hits on tracks. So on the left is the number of pixel hits per LRT track. On the right is the number of STT hits. And we see good modeling again in both of these distributions, which is quite promising in case these variables wanted to be used as, for example, input to low-level LLP taggers, which could offer quite a good discrimination. And the modeling is important to make sure that these quantities are have good agreement between data and Monte Carlo. So this is quite promising. So now taking this one step further, we can actually then look at a more high-level quantity to try to actually probe what the LRT efficiency looks like in data and compare that to Monte Carlo. And so we can do this by taking K-short decays as kind of a standard candle of a standard model along with particle decay, and actually reconstruct these and try to probe how many vertices are being reconstructed in data in Monte Carlo. So we do this by reconstructing 2-track vertices using the combined collection of standard and LRT tracks, and then requiring that these vertices have an invariant mass with a 25 MeV window of the K-short mass. For now, we're not applying any additional background rejection or subtraction, but this will be investigated in the future. And so we can look at this after normalizing the Monte Carlo to the data. We can break down the distribution of the radial position of the K-short vertices in terms of whether or not they have 2 standard tracks, 1 LRT and 1 standard track, or 2 LRT tracks. We can see that overall we have extremely good agreement. The distribution in data closely matches the Monte Carlo performance. And after the IBL and the first pixel layer, the LRT tracks start to become dominant and are a clear indicator of the importance of this algorithm in reconstructing some of these more displaced signatures. So we can kind of take that previous plot and look at it in a slightly different way by normalizing each of these distributions by the total number of K-short vertices. We can kind of take a look at the fraction of this distribution that is that is reconstructed using LRT and without using LRT. So in the green and the black markers are the standard tracking K-short candidates, the fraction of them, and the red and white are the LRT candidates. And so you can see that after roughly 30 millimeters in displacement, the LRT brings a clear benefit. And after the 3rd pixel layer, the LRT vertices account for roughly 90% of our K-shorts. And so once again, we have extremely good agreement in these distributions between data and Monte Carlo, which indicates that there's no systematic differences observed between the LRT performance in data in Monte Carlo. And so work is ongoing to kind of use these studies to actually derive our systematic uncertainties on the LRT efficiency to then be used as input for LLP analyses downstream. So just to conclude, large radius tracking has been completely overhauled in preparation for run 3. We have a 95% reduction in fakes with only a 10 to 15% reduction in signal efficiency. This massive speed up from this fake rate reduction allows for LRT to be included in the standard Atlas reconstruction chain, which significantly simplifies the workflow for LLP analyses, as well as allowing non-LLP analyses to benefit from LRT. preliminary data Monte Carlo comparisons show extremely good modeling of various low-level track quantities. And most importantly, these updates will completely revolutionize the Atlas long with particle search program by improving our performance, our signal to background ratio, significantly increasing our flexibility, and hopefully allowing us to do more physics. So thank you.
Questions? Quick check on Zoom first. Look like it's in the room.
Yeah, this is Michelle. So on the slide 12, why does it increase again if you go to very large data?
So once you start to get outside of the first SCT layer, you no longer have enough hits to pass the LRT tracking cuts. And so you start to be starting to get dominated now by backtracking. So you start to have standard tracks taking over again once you no longer have enough hits to reconstruct an LRT track. Yeah, good question.
Paulo, you had a question?
Yeah, somebody is more urgent. Well, I'll ask it. So is it possible to do large radius tracking outside the inner tracker and the TRTs or even farther out?
You would really start to lose your resolution without having hits in the silicon, and your fake rate would start to be considerable again. But yeah, to my knowledge, that's nothing that we've necessarily looked into. But I think that for run 4, the ITK is going to allow for, with more silicon in the detector, you'll have a better resolution and be able to extend LRT outside of the 300 millimeters that we have now. So
there is in Atlas one dedicated reconstruction that looks for signatures where you would have very large radius tracking, so tracks that originate muon tracks mainly in the calorimeter by muon standalone tracks, which you then feed into a 2-dimensional vertexing, and you basically find the vertex. This is under some SUSY models you can have this sort of signature.
Yeah, displaced muon vertices. Yeah.
But that's only done in a projection plane, as far as I know.
I believe so. Yeah.
Good. Any more questions? Otherwise, Jackson, thank you very much.